So one thing that I notice as a student, if I were a student, I'd notice down here, that's, call it a symbol. And these are in your symbol, the back of your packet, don't forget, you got about 44 different symbol, I call them symbols. And definition, that would be the definition is chi-squared. What the heck is a chi-squared? It's a Greek letter of the alphabet. Chi. Just not squared, but that funny X is called chi. Alpha, beta, gamma, sigma, blah, 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 pi, chi, C-H-I. Okay, so that's going to represent something. That's what you're going to learn. So it's just called a chi-squared test, not a t-test, not a z-test, a chi-squared test. And what we're doing is we're going to target or focus our attention on the population standard deviation rather than population mean or the average.
Hey, Jeff, in the back of the book, you have it as x squared data.
Well, chi-squared data.
Okay, that's how it is in the back.
Oh, yeah, and that's okay. Well, let's see. Hold on a second. Let me. Okay, let's take a look. Let's see what I did. Yeah, so I see chi-squared with the word data. If I saw chi-squared, then you'd say chi-squared. This right here with the data is a data number that you guys have seen, like a T data, Z data. It's called a chi-squared data. And the definition is the chi-squared test statistic. The other one would be a Z test statistic. Yeah, I guess if you want to call it. Let's see what I said here. There's so many of them here, aren't there? Let's see if I've got one here. Yeah, I don't have any other data values, do I? Okay, I'm going to go back and show you about the author's previous chapters. Oh, give me a second. Get my books here. We call it a test statistic. I can't say that 3 times fast without slobbering all over myself. Test statistic. Instead of saying data value, it means the same thing. Test statistic. It's like a formal definition. All right, let's go into 9.2. Test statistic. Statistic. Yep, there it is. Okay. Page 499 has an example. There's many other example locations too. Okay, so Z data test statistic. So chi-squared data test statistic for the chi-squared distribution. So if I said formally, based on my packet definition, you must word for word do that, then you're going to go with my packet definition. But the data value is the chi-squared test statistic. All I'm doing here is saying that funny X is the word chi, which is actually a Greek symbol, and the power of 2, another way of saying it is square or squared. So how you read this, not as a definition, but as a reading it, chi-squared. It's not a definition, it's chi-squared. So if I said definition, then the definition in the back of the book or the back of my packet's the best. All right, the normal, well, look, it kind of looks like a normal, but no, it's skewed. You see how that's not a bell shape. Nope, nope. So there's nothing about normality. It's not symmetric. See right here, not symmetric. Nope, 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 nope. And it is continuous, and that's the reason is if the picture here is indicating that there's a gap at the end. The shading goes forever on the right-hand side. The tail is open all the way to the right-hand side. However, over here on the left, you can think of this as the number 0. All right, here's something else for you. Anytime you square a number, do you ever get negative numbers? If I said with parentheses, any number squared always gets you a positive answer. Including 0 is not positive, it starts at 0. So 0 starts right here. So close your, when you draw a picture, you know, you can go like this. I'll do that, and then I'll start it right here and just kind of pile it up and then flow it down here, make sure there's a gap at the end. That's what you're going to do. You're going to have one tail and two tail, just like we've had before. You'll have a hypothesis test you got to set up, a one tail test and a two tail test, and you can tell it the same way, because if it's a less than, it's a one tail left, and if it's a right tail, it would be a greater than. A one tail left would be over here, shading over here. Even though the tail isn't forever, it would be a chunk over here. That's a one tail left. This is like a one tail right, and there is a two tail. It's just not symmetric. Degrees of freedom is still n-1. That's familiar. The area under the curve is still 1. 100% is all of it, all of it, all of it, just like the normal. It's all of it. But for chi-squared, we're dealing with standard deviations, not with the mean. That's the difference. What else about this before I get started on the next page? Oh, table. I'll show you the table. I should have printed one out and had it copied in the back. It's in your textbook too, the table. It's called the chi-squared table. So we're not using the same table as we did with the other chapter problems, okay, which this is the one we've just been using here. Go to the page right after. Oh, there it is right there. See, it says chi-squared right there. So this is the table we're going to use for 9.6. That's what you want to write here. Hey, this is 9.6. That's the only time in our course we're going to use that table, and it's for 9.6. I'll have to show you how to read the table when we get there. So dog ear this. I'm going to dog ear this to make sure I easily can find that. Back to my problems. Too numerous to count. Go back to my problems, my own problems. You have yours and I have mine. And mine are too numerous to count. Ha, ha, ha. No, math problems. Yeah. Okay, that's stupid. All right, let's just finish up the rest of the semester, Jeff, without any kind of crazy jokes, and quit talking so much, Jeff. Okay, I'm going to try. No promises, but I'm going to try to stop talking so much. Yeah, there's only 2 weeks left. I'm sure a lot of you are grateful that you're not going to have to hear me ramble on like I'm doing right now. Leave you with this. Let's flip the page and see what we got now. Degrees of freedom, don't forget. All right. So the critical number comes from the table, just like the last time. You look at the table, come with the critical number, degrees of freedom. Normal population. Okay, we assume normal on all of it. You're not going to have to test for it. These are normal. It's a small little section that if you took a higher level statistics course or some other course that's going to need a higher level class, then you would probably have to go through a testing of whether it's normal or not. But we're just going to assume that. Now, a dot plot can be used to test normality, just as an idea. But again, I'm not going to do that today. We're just going to assume normal and everything. The data value there's the formula. You will be given sigma sub naught. That's like the given historical population standard deviation. You will be given that. And somehow you're going to have to either be given little s, or you're going to have to calculate it using your calculator, one or the other, if you use the formula. Lowercase n, of course, is going to give you what n is and degrees of freedom. So when you do this formula, you're going to get a number, but our calculator will also, again, produce the number. So I'll show you how to do that. So you don't have to use this formula if you don't want to. Okay, you get three potential hypothesis testing scenarios, just like the other one. You got a left tail, right tail, and a two tail. So I've got this little chart. If I started off with this, you know that H sub A would have to be the other notation. And then this would be a sigma, not a mu. Sigma, this would have to be greater than, no equal sign on this one. Sigma sub naught. And the tail is based on the alternate. So that's a right tail. Let's say you're given this. And gosh, that's a left tail. Well, this one's a left tail. Then you go H sub naught. And then you go sigma and greater than or equal to. How about just equal to, Jeff? Yes, the author, again, does just equal to. Same with this. It'll just do equal to. It's your choice. And this would be sigma, so not, but the tail decision is based on the alternate. And over here is a two tail. A lot of similarities from section 9.2 to 9.5. Now, the statements up here about when to reject the null, the statements right here, all this is doing without the picture, without drawing the stinking picture with the shading. If you did the picture, you're gonna have to have the critical number. Okay, you're gonna find it. Okay, that's a there's a crit. Okay, so you can write sigma squared. I said sigma, sorry. Oh my gosh. Chi squared crit. It looks like there's an alpha, and that is true, but you could write in place of the alpha, just call it crit. Critical number is the same as the alpha. It's the same thing. All right, so if I looked at this, all this is saying if your data value is bigger than a right tail critical number. So if it's a right tail critical, your data number is in the rejection region, it's in the shaded region, just like before. It's just not showing the picture. So this would be like if your data value is in the rejection region, then reject the null, period. This is saying the same thing. If your data value is in the rejection region on a left tail, that's a left tail. So if you have a left tail, the data value is smaller in the left rejection region, then reject the null. And then this one here is saying if your data value is either in the one tail left or the one tail right, reject the null. So picture-wise, I'm just not drawing the picture, but it's the same idea. The p-value is exactly the same. We've had, find the p-value, use your calculator again. You'll see where I do that. And if it's less than alpha, reject the null. If it's not less than alpha, you don't reject the null. And here's your calculator instructions that I'll even show you right now where to find it. And reminder, your calculator instructions is always multiple places, lots of places. I just put it here as an example. In your textbook, 9.6. Here it is, down at the bottom. Might be slightly worded differently, but there it is. So it's there. And there's one other place in my packet. Jeff, I forgot where those instructions are. I know, or somebody's not here today and they're not getting they never read my video or watched my recorded video. And I'll just shake my head and I'll say, it's there. It's 3 different places. You guys look if they email me. So I don't know where this thing is, calculator instructions. Well, of course, YouTube has probably That's probably the first place that I would go to anyway now that I'm thinking about it. Okay, so, okay, oh, here it is. Chi-squared number 9, Roman numeral number 9. So I've given it to you, well, in 2 places in my packet, and I've shown you 1 place in your textbook. Okay, so let's just go ahead and follow here, just to see where it is. Okay, second distribution. Okay, we're back over here, not stats, but second distribution. Second distribution. Okay, so I'm looking for chi-squared. Oh, it kind of feels like, which is true, it feels like the normal distribution, but it's not. I'm not going to pick number 2. I'm going chi-squared. There's the PDF right here. See, there's the PDF. Don't pick the PDF. I never use the PDF in my course. There's the CDF that you want, which is saying right here. Hit enter. And then it's got a few things. And so over here, I think I said on the home screen, enter the value of the data value. So what you're going to do is you're going to do the data value and then put a comma and then do really big number. Now, if this is a right tail, that's what you do. If it's a right tail, I should probably emphasize this. Right tail. If it's a left tail, you smart with the smart. Yeah, we're smart. I'm not very smart saying that. You would start at 0 if it's a left tail. 0. That's the smallest number on that picture. And then you go to the data value. So it just reverses. This would be 0, comma, chi-squared data, comma, and then degrees of freedom, and then close your parentheses. And what that will do, it will give you for sure your p-value. Actually, that's all it's going to do. It's going to give you a p-value, period. So this will give you a p-value. So now I'm thinking about it. Your data value, the only way you can get your data value is not by calculator, is by the formula. The only way, if you're going to do it by the kind of the curvy thing with the picture, the only way you can get your data value is not with the calculator, it's with the formula. Just keep that in mind. P-value gets you result, reject or don't reject the null. But if you ask for the picture, then you're going to have to go to the table and do your picture, do your shading and all that stuff. But the data value must be found by the formula. I can't come up with any way of doing it with the calculator. Let's see, what do I want to do here? Yeah, I can do this. So, pictures. No, okay, crit. I'm going to show you something. I call it crit. Kind of important now that I'm thinking about it. This one here is crit alpha. On the right, it's crit alpha or chi-squared alpha. Over here, it's 1 minus alpha. And I'll show you on your table. So 1 subtract out. So it's the complement. There's big difference on how you pick your critical number from the table. And then on a two-tail, you have like this, maybe like this. And this would be chi squared, and this is a chi squared. And down here is still the 1 minus alpha, and over here is alpha. And then you still got the shading in the tails.
So Jeff, the tails are connecting on the left there? Or
Yes,
they
remember
aren't?
that's 0. Remember that's 0 right here. That's a 0. That's a 0. That's a 0. That's a 0. They are touching the x-axis. They are not touching on the x-axis on the left-hand side. They are not touching, so to speak, the x-axis on the right-hand side.
Okay, thank you.
Yeah, so don't look at the tail like it's I understand this is confusing maybe. Hey, left tail, that means it should feather out and never touch over here. No, left tail is the shaded region, is on the left. The shaded region is on the right. It just happens to go forever this way. Forever. The left tail over here just stops at the origin.
That makes sense.
And is the area on the two tails still the same, like still equal on both sides?
Okay, good point. Now, if alpha was equal to, let's say 10%, I'll just use that and use it as a percentage rather than as a decimal. Decimal is 0.1. But alpha's 10%, then this amount here is 5%, and this amount is 5%. Just the pictures look a little off because it's not symmetric.
Okay, that makes sense. Thank you.
If alpha is equal to 10% here, 10% is all of this, and 10% would be all of that. But otherwise, you have to split it up evenly. It's just the shaded region will look weird, not the same, but the area, if you could figure out the area using, it's like the area of a rectangle. I know how to use formula. Here, you don't have a way of figuring out the formula. You just know that this area right here is 5%, and this area right there is 5%. So together, it's 10%.
Thank you.
Yeah, good question. I'm going to look at the table, show you the table now. Did dog ear this somewhere? I did. Certainly I'm making it easy on me. Okay, maybe it's back over here. Oh, there it is. So I wrote alpha over here for some reason. Here's your alpha. Okay, so do you see how it looks like there's big numbers over here and there's small numbers over there? If I cut this like in half. If I add these together right there, isn't that 100% right there, those two numbers?
Yeah.
Those two numbers are 100%. These are complements of each other. Complements of each other. And again and again. So maybe you might say, really, these are your alphas there. I like this better now that I'm thinking about it. Where's my white? Oh, here's my whiteout. Instead of that, make this 1 minus alpha over here. So you're going to be given an alpha that's pretty typical. These are going to be the small numbers like 0.05, 0.01, things like that. So what's the complement of 0.01? It's 0.99. Oh, over here. If it's a two-tail, you've got to use both of these numbers. if it's a two-tail, you have to go down these separate columns because the left part of the two-tail is over here and the right part of the two-tail is over here. See how, look at the numbers. Like if I went across here, 26 is bigger than 3.5. So on the number line, this is close to 0. So this is going to be the left part of the tail because it's close to 0. This is the right part of the tail because it's way far on the other side. Now, what if it's a one tail right? One tail right is this. So this would be, this is for sure one tail right, one tail right. And over here would be a one tail left. So if you have one tail left, you want to look over here. But understand, you're going to be given an alpha. So if you said, hey, alpha is 0.01, then you have to look over here and there's no 0.01. It's the complement. So, oh, that's the one I want right there. That's the complement of 0.01. And then you go down here for your degrees of freedom and whatever it is, you stop and that's your critical number. Your critical number. Okay, so let's go over here, flip the page, see what I got. Okay, you don't need this. This is just information. Oh, okay, let's try to find the p-value. Let's do this one here. Okay, n is 10, degrees of freedom is 9. Alpha is 0.05, great. And it is, what am I going to find? Find the p-value. The data value is this. So p-value is always found by taking the chi-squared CDF. Here, I'll show you again. Right here, this is finding the p-value. Gives the p-value. This right here is the p-value. So I'm going to go chi-squared CDF, and depending on the tail, let's see, the tail I have here, it is a right tail, one tail right. So I'm going to start at the data value and go forever as big as I can. Stop, which would be infinity. Do this, I'll set it up before I find the, so you're going to, it's like this. Right here, forever. That's pretty symmetric. Don't like that. Okay, try it again, Jeff. Pile it up. Okay, better. Okay, data value. If it's a one tail right, you're going to go like this. This is your data. And shade, shade, shade. And this is your p-value. Not the critical number, the data value. So then, okay, the data value. Here is 20.12. So you do chi-squared CDF. Your left then is 20.12. Your right is infinity. Well, pick something ginormous, like 10,000, like what I've taught you in the past. So there's only 3, and there's no standard deviation. There's none of that for this. It's a left, it's a right, and the other one is degrees of freedom. It's the 9, not the 10. It's not N, it's DF. It's DF. Oh, so you go chi-squared CDF 20.12 big comma 9. Squiggle squiggle p-value. This is your p-value. Okay, let's find this. Oh, got it here. Nice. Had it here already. Okay, so 20.12. Upper is like ridiculous. The freedom is 9. Paste. Enter. P-value 0.0172. Which, if you were asked to compare it with your alpha, don't know what my alpha is. Let's say you compared it to 0.05. Well, that's smaller than 0.05, so you'd reject the null. What if you compared it with 0.01? Different decision. Don't reject the null. This is actually bigger than 0.01, not by much, but bigger. See, so that's the idea. Okay, let's see, determine whether we reject the null or not. All right, let's see, this is a one tail right. This is a right tail. Okay, to determine that, if I had a p-value, then in an alpha, but Jeff, you're not giving an alpha. Well, okay, if you're not giving an alpha, then you just use 0.05. If I had a p-value, then I can determine this. How do I find the p-value? I have to have a data value. Oh, the data value. Now, how to find the data value? The only way you can do it is the formula. So what you have to do is the formula. So formula, the data value. It's a fraction. And I ain't forgotten. I want to write it down correctly. I've forgotten it. Okay, where is it? Here's it. N minus 1 s squared sigma sub naught squared. N minus 1. N minus 1. So N minus 1. This right here is sigma sub naught. Right there, sigma sub naught. So you got everything. All I have to do is just go, N is what? Oh, maybe I don't have N. And I have no degrees of freedom. I don't think I can do this one. I have S. I have to fix this one for the next semester. I have to have an N. I'm going to pick N to be 26 down here just for the heck of it. It has nothing to do with the top problem, but okay. What if N is equal to 26? Oh, then what you're going to do is you're going to go 26 subtract 1, and then you got 2.990354866. I'm going to be as accurate as possible. And that's 2 squared. Squiggle, squiggle. Calculator.
Don't we square the S? Don't we square the
Thank you, I
2
did.
point?
Yeah, thank you. I didn't do that. Yeah, good catch. Yeah, good catch. So 55.89. Okay, now what I could do is use both. I can use two things. If you assume that alpha is equal to 0.05 because alpha wasn't given, you can do two things, and we'll see if they agree. You could use your table to find the critical number and then compare to see if that's to the right or to the left of that critical number. And that'll help you make your decision. The other way is, since I have a data value, then I can use, and I know it's a right tail, then I can use my chi-squared CDF and get a number, p-value, and hopefully the same decision. So I'll do it both ways. I'll do table. And we need a crit. And since it's a right tail, I just use the alpha 0.05 since it's a right tail. Since it's a right tail, I use my 0.05. My degrees of freedom was 25. So I see 37.652. 37.652. 37.652. So on a number line, if I did shading, isn't this farther to the right than that one? The data value is farther to the right than the critical value. So it's a reject the null. Reject. Now I'm going to look for the p-value. And if it's a reject the null, the p-value better be small, smaller than alpha, smaller than 0.05. So in my calculator, let's see, I go into second distribution, chi-squared, CDF. So it's a one tail right, correct. One tail right, I got to put in my data value, which is, that's the data value. And something ridiculous, which is that, degrees of freedom, however, it's going to be 25, paste, enter. Small, 0.000, 3 zeros and a 37. Small. Yeah, so squiggle. We'll go 3.8. And so, yeah, that's less than alpha. So again, reject the null. And if it was a word problem, you put a little wordy sentence at the end to talk about the alternate. You're always talking about the alternate. So if you reject this, then there's enough evidence for this. If you don't reject that, there's not enough evidence for that. That's how it went in the past. That's how it goes here as well. Okay, let's see this one here. This is a two tail. They gave me that. They gave me that. Okay, they gave me a lot. That's good. Draw a curve. Okay, two tail. So you need to find here and there if you're going to draw a curve. These are both critical numbers. These are your shaded regions here. Sorry, you can't see that. There you go. So if it's a critical, oh, an alpha. Alpha is not given, so we're going to use alpha again to be 0.05. Okay, go into the table. Degrees of freedom again is 25. DF equals 25. Well, that's convenient. I think this one was already degrees of freedom. Let's see. 30. I should find 37.652 again. I should find that. There's another number that goes with that though. So I'll show you how to do that. 0.05 two tail. 0.05 two tail. Okay, 0.05 two tail. So this is going to be the right hand one. And I got to go down to that 25 again. And sure enough, there's that same number, 37.652. The other one, since I'm two across this blue center line, I should be over here, two across over there. Just to confirm, these two numbers had better add up to 100%, and they do. So here's that number again. I'm going to use 14.611 along with 37.652. 14.611. This number right here is 14.611, and this one here was the 37.652. Now in order to use the picture, I have to have the data value no matter what anyway. And the data value will help me find the p-value if I wanted it. So data value, it's all about the data, or what do they call it? The test statistic. Chi-squared test statistic, or chi-squared data. Chi-squared data. Okay, equals, okay, that's an n minus 1, little s squared over sigma sub naught. Oops, sigma sub naught squared. Okay, my n is 26, s is 5. Oh, so is sigma sub naught. Remember, this is sigma sub naught. Oh, gosh, I do that a lot, don't I? I've only done it twice, but that seems like a lot. Okay, so sigma sub naught is also 5, where just so happens standard deviation is 5. So 5 squared. These will go away. 25. At the end, it's 25. Didn't have to use my calculator on that. So where's 25? It's in between here, somewhere right there. There's your data. There's 25, which is your data. So from that point of view, you're going to say it's don't reject the null, fail to reject the null. Now the p-value is a little more complicated. Trying to think if I should even go the direction. I'd have to go to the formula in the textbook. It's more complicated because it's easy if it's a one tail, because you would say, the data value, if it's a right tail, you go all the way this way. If it's a left tail, you go all the way that way. But what if it's a two tail? Yeah, it gets complicated. So I'm thinking, I'm not going to give you one on the final exam. What am I not going to give you? I'm not going to ask you for the p-value for a two tail. I can ask for a two tail picture and ask you to make a decision, and the only way you're going to do it is with picture, data value, critical numbers. That's the only way you can do it for the decision. But to ask for a p-value, it's just too, I'm confused. I get confused on how to find it because I don't use it that often. Does that make sense? I'll say it one more time. No p-value will be asked of you for a two tail. But that's it. Everything else will be asked of you in this section. Okay, I got one word problem, and I think that might be it for this section today. Oh, and by the way, we're done with our little baby quizzes. Those daily quizzes, they're done. I have all 10 of them. So we're finished with that. All there is just a group quiz in about a week and a half, one group quiz, and then your final exam. And those of you who want to turn in your homework, you got one more homework that you could turn in. But so home stretch. Does the growth rings of trees, excuse me, I said it wrong. Does the growth of trees vary? Okay, now the word vary feels like variance. And isn't variance defined like the standard deviation squared? So that's kind of a signal here that if you're looking at, let's say, the group quiz or the final exam, what are you keen on in terms of a hypothesis test? Got to have the word mean in there. Something about a proportion. And now you got this thing about variance. All you got a standard deviation. You don't have averages, blah, blah, blah. Okay, so vary. when tree is young. The International Tree Ring Database collected data on a particular 400-year-old Douglas fir. Anybody been to, I think they still have it outside, Mead Clark Lumber in Santa Rosa? Okay, good. So Peyton's saying yeah. So they used to be out in front, I've been there for a long time, out in front of their big double doors when you enter, on a cart or something, a ginormous cut of a tree, not a trunk, the whole trunk, but a slab, and you can see the rings in that. They've got one there. That's very interesting. So, you know, you probably have heard about, you can figure out the tree's age. I've heard that before, foresters, if about the rings, the tree rings. So standard deviation. Okay, how in the world they get the standard deviation? That might be a good question. You know, how would you do that as a statistician for the U.S. forestry? But they're going to give you information. Someone gave it to you. Standard deviation annual tree agreement in the first 80 years of life was this. Okay, that's going to be your little S, because it's the first 80 years. It's not all of it. It's just the first 80 years. S equals 0.8 milliliters per year. Assume normal. Okay, that's helpful. That's good. Interested in testing whether the population standard deviation, so that's sigma. We're interested in sigma. We're interested in comparing sigma with something. In its later years is less than that. We're wondering if the tree's rings variance is less than the I got this wrong. I've got this wrong. This is sigma sub naught. Because that's like the first part, or hysterical. That's the historical. That's like what you're comparing against. So my mistake. I apologize for that. This would be 0.8, and this is 0.8. That's what you're comparing. I wonder if it's less. Okay, now I got to put in something over here, don't I? How about equal 0.8? So that's a left tail. Hard to see the notation, at least my copy. I don't know about you. This is 1 minus alpha. Hopefully you understand what they're trying to tell you. When you do the critical value and it's a one tail, you have to look at that left, those left columns of numbers, the left columns in the table. Okay, 0.05, n is 100. Okay, that means DF is equal to 99. Here comes the table. Left tail, okay, left tail. Okay, 0.05, but the complement of 0.05 is 0.95. Or you can say, here's 0.05, but it's left, so I have to go kind of a reflection over here. Oh, 0.95. Now I'm going to go down to 99. 99, 99, 99. There ain't no 99, Jeff. Yeah, so pick the closest one. Okay, 100. I'll pick the 100. It'll be close enough. Okay, so 77.29, 77.29, 77.29, 77.29. There might have been another digit there.
It's 929.
Thank you very much. Yeah, 77.929. Oh my gosh, I need to go home. Now, if it's a picture that we want, it doesn't say that, but if it's a picture that you're supposed to do, then you're going to go something like, okay, left tail. Yeah, this would be your 77.929 and shade over here. That's what it would look like. Now, it says the sample variance, sample variance. This is your that's true. That's the variance, not the standard deviation. So if you wanted the standard deviation, you take the square root of it, which would be whatever that is. But I'm going to keep it right there. Here, look at the formula for a second. You didn't know this, but it's true. See what I'm pointing at in the formula? I said that's standard deviation squared. That's variance. This is variance. That is a standard deviation, so you'd have to square that number, but they're giving you in this problem, or I'm giving you in this problem, the variance. So if I'm going to find the data value using the formula n minus 1 6 and over this, then that's 100 subtract 1. This number is what you would put there, no squared, because it's already been squared. And all over. Okay, sigma sub naught was 0.8. Squiggle, squiggle. All right, now, knowing that, I have to do this by hand. If I haven't made a careless mistake, that's your data value, which again is a left tail. Think left. Because when I want to compare. Oh, I was going to do my p-value, so forget the p-value. I want to compare them. So where is this sitting in comparison here? Isn't it to the left? Yeah, the data value is smaller than the critical number, or it's in the rejection region. That's the other thing you can say. Hey, this data value that's right here in red is right there, a dot on that side, the left side of the 77, but to the right of 0. So that is there. Oh yeah, it's to the left. Data value is to the left. So reject the null. Reject the null. All right, interpret or summarize or conclusion or something. So if I reject the null, then there's not enough evidence. No, excuse me, there is enough evidence. If I reject this, I don't want that. This is what I'm trying to show. Yeah, so there is enough evidence to determine that and then you put that in words at the end. There's enough evidence to suggest, someone gave me that word a couple times. I like it a lot. Instead of saying support, instead of saying determine or show, I like suggest. That what? The annual ring growth, that the annual ring growth in the tree's later years, later, tomato, potato, Gurneyville, I don't know. Latter years is less I did something weird at the top. Millimeters is right notation, mm, millimeters. Way at the top, I went ml. That's like milliliters. So I make, okay, way up here, way at the beginning. I just noticed that's wrong. That's bad. Millimeters, mm per year. I corrected that. Is less than millimeters per year. So I think I am done.